Okay, 2016 AMC12A question number 6. A triangular array of 2016 coins has 1 coin in the first row, 2 coins in the second row, 3 coins in the third row, and so on up to n coins in the nth row. What is the sum of the digits of n? And I'll use the formula to get the solution. If that's good for you, move on to the next video. If you want explanation on why the formula is true, I'll show that at the end. So here's the idea. I have an arithmetic sequence for the number of coins in each row, and the sum of any arithmetic sequence is going to be the first term plus the last term multiplied by the number of terms divided by 2. And since I'm going from 1 up to n, counting by ones, there are also n terms. N is the highest term and the number of terms. And I say that's going to equal 2016. And so now I can just solve for n and then find the sum of all of its digits. So I'll multiply through by 2 and distribute the n. So I get n plus n squared equals 4032. And then I'll get n squared plus n minus 4032 equals 0. Now when I saw this originally, I saw that these added up to 9, but it's not the value of n. So I actually worked my way through here, but I saw that I have one n here. So I'm going to have n plus some number times n minus some number. And the plus has to be 1 greater than the minus, so I'm left with one n in the middle. And they need to multiply to negative 4032. And so I tried a couple of things. Let me think back through what I did. So I did this. I tried to sort of take the square root, because if one's higher and one's lower, I'll get there pretty quickly. And I said, okay, what's 50 squared? Well, that's 2,500. Too low. What's 60 squared? That's going to be 3,600. Still too low. What's 70 squared? Well, that's going to be 4,900. Much too high. So let's go back to 60 squared and consider, okay, what is 62 squared? 62 times 62, let me actually rewrite it as this multiplication. And that gives me 4, 12, 2 carry the 1, 36, 7. So that's going to be 3,844, still too small. What's 63 squared? So 3 times 3 is 9, 3 times 6 is 18. 8 carry the 1. And I get here 9, 6 carry the 1, 9, 3, 9, 6, 9. And when I do 64 times 64, I already know this from other work. 64 is 2 to the 6th. 2 to the 12th is 4,096. It's too big, and so I'm going to have n plus 64 and n minus 63. And just to make you believe, 64 times 63, 2 carry the 1, 19, that's a 9 there, 4 carry the 2, 38, and from here I get 4,032. This gives me two solutions, negative 64 and positive 63, and it has to be positive, so n equals 63. The sum of those digits are 9. If you get this, move on to the next video. If you want, a quick note on this. So why is this the formula for the sum of a finite arithmetic sequence? Well, let's consider the sequence 1 plus 2 plus 3 plus 4 plus 5 plus 6. Sure. Now that's not too hard to do by hand, but this is much more difficult than doing something like 2 plus 2 plus 2 plus 2 plus 2 6 times, because that's, sorry, not 6. That's just going to be 12. 6 times 2. These are changing. What I need to find is something called an invariant, something that's not changing. And in arithmetic sequences, if I take the outer two terms and add them up, I get 7. If I take one step in and add them up, I get, in this case, 7. And add them up, and I get 7. And so, no matter how this works, because going up this way and going down this way add and subtract the same value, these will be invariant, and I can end up doing the sum of the first and last term times half the number of terms, because each one of these takes up 2 terms. So that's why this formula works. Feel free to comment below with any questions.